Hello, I'm Yoder.
And I'm Huang.
We will be summarizing our efforts in reproducing and verifying the results of a recent research paper that proposes a novel approximate multiplier architecture named High Performance Approximate Multiplier, or HPAM. First, let us review the use case of approximate multiplication. Multiplication architecture typically is broken down into three stages, which include partial product generation, rearrangement, and compression of the partial product matrix, and finally, the accumulation of the result. Each of these stages require a large amount of hardware, including many AND gates and adders to generate the partial products and compress or accumulate them. With such a large amount of hardware, significant power and delay results from multiplication operations. But what does any of this have to do with approximation? Well, in some applications, such as many image processing algorithms or in areas of machine learning, exact values are not necessary. We call these error-resilient applications. If we can replace the multiplication operation with a good enough approximation, we can significantly reduce delay, power, and area for these applications handling large amounts of data.
The HPAM approximate multiplier differs from prior work in that it targets 8-bit multiplication, which is useful in image processing applications. The paper uses the conventional Wallace tree multiplier design as a baseline, so we started with a Verilog implementation of that. To convert the Wallace tree design into HPAM, we just had to apply the stage 2 and 3 approximations detailed in the paper. This included inverting the left half of the partial product matrix to minimize the number of adders used, as well as setting the least significant 4 bits of the 16-bit result to 0, a method called truncation. Furthermore, the proposed segmented ripple carry adder, or SRCA architecture, replaces a section of the regular ripple carry adder in the accumulation stage, resulting in a portion of the least significant 8 accurate full adders replaced with approximate ones. How many is what distinguishes HPAM variations, with HPAM4 employing 2 approximate full adders and HPAM2 using 4.
Mean relative error distance, or MRED, is a metric used to compare error between approximate multipliers in the paper. The paper shows an MRED of around 0.035 for HPAM2, while we saw an MRED of 0.030558 for HPAM2. The paper also shows an MRED of a bit under 0.02 for HPAM4, and we saw an MRED of 0.018608. The slight difference are a result from the paper calculating MRED on a large dataset of random inputs, while we calculated it on the set of all possible input pairs.
One thing to note is that we use the SkyWater Sky130 PDK, while the paper uses the NANDGate 45nm open cell library. So it is kind of tricky to compare PPA metrics. However, we did see good speedup when pushing each design. With the Wallace tree, we saw a data path delay of 17.7 nanoseconds, and with HPAM4, we saw a data path delay of 4.945 nanoseconds, which is a huge 72% decrease from the Wallace tree design. With HPAM2, we saw a data path delay of 4.353 nanoseconds, which is an 11% decrease from HPAM4. The HPAM designs also take an average of 18.3% less area than the Wallace tree design.
The paper also shows peak signal-to-noise ratio, or PSNR, and structural similarity index measure, or SSIM metrics, from running the designs through an image sharpening algorithm. We were able to get MATLAB code of the sharpening algorithm they used and re-implement it in Python. We used lookup tables generated from our test bench to emulate our designs in Python. The sharpening algorithm includes a matrix multiply step of a 5x5 Gaussian kernel and a 5x5 section of the image. We realized that the HPAM designs do not preserve the commutative property of multiplication. The paper does not discuss the missing commutative property, but we found that it actually has a substantial effect on the results.
We collected 2 sets of data with flipped operations, one with the kernel as a left operand and the other with the image section as a left operand. The difference in results is most evident with HPAM2, which performed much worse than HPAM4 with kernel times section, as in the paper, but strangely better than HPAM4 when using the section times kernel orientation. Our results are similar to that shown in the paper when using the kernel times section version. The PSNR they achieved on HPAM4 is higher than what we observed, but our value of 36.67 is still above all the other approximate multipliers in the paper. The same goes for SSIM. It is important to note that the example image the paper uses is rather small, around 256 by 256 pixels. While a smaller image like this sharpens well with the HPAM architecture, when using a larger image, we notice artifacting. For example, in the sky of this picture of Jared at Mount Fremont Fire Lookout.
There are some goals of this project that we did not fulfill in the time we had. One goal we identified early in our project was to compare HPAM to other approximate multiplier designs. However, this proved to be more of a challenge than we had hoped. In particular, we wanted to compare the same approximate multipliers that are referenced in the paper. We hoped that we could find open source implementations of these multiplier designs, but we came up with nothing in our search. With the time we had left, when we realized this was the case, we had to choose between re-implementing these other designs or showing an application using HPAM like the paper did. We chose to pursue image sharpening using HPAM. Overall, we have successfully recreated the proposed HPAM architecture, confirming many results and trends that match what was reported in the paper. However, we also found some problems with the architecture that were not discussed in the paper, like the non-commutative property and noticeable artifacting.
Thank you.